Hello, good evening. Am I audible?
Yes, ma'am.
Okay. Okay, so let's start today's session. So welcome to week 12 of the tutorial session of the course control systems. And this is the last week of the NPTEL course. And this is the second last session. We will have one more extra session in next week. So in today's session, we will go through problems based on compensator design, Ladley compensator. So let's get started. So this is our first question about the lead compensator. Identify the correct statement about the lead compensator. Okay, so before solving this question, let's have a quick recap of what lead compensator is and what does it do. So for a lead compensator, we know that its transfer function looks like Kc into alpha 1 plus St divided by 1 plus St alpha. Okay, and from this transfer function we can conclude that instead of time constant form, we can convert this into time constant form by dividing alpha. So this will be s plus 1 by t. Okay, and from here we can identify that there is a 0 at location minus 1 by t, and there is a pole at location minus 1 by alpha t. Okay, so we have a pole and a 0, and since alpha belongs to 0 and 1, we can conclude that if we draw the pole 0 location, we will have a 0 nearer to origin and a pole away from the origin to the left. Okay, so this is your minus 1 by t, and this is minus 1 by alpha t, because alpha is between 0 to 1. So this is how the pole and zeros of a lead compensator looks like. Now with this pole and zero structure, if we draw the Bode plot, we can see that, so this has been already covered in the lecture by professor. We are just going through a quick recap. Since we have corner frequencies at 1 by t and 1 by alpha t, so this will have a Bode plot like this. So these are your corner frequencies. This is Gc of j omega, and this is log omega. And from the Bode plot, we can see that this attenuates the high frequency component, a low frequency component, so it acts as a high pass filter. And if we see the if we calculate the phase of this transfer function, what we will observe? We will observe that it introduces a positive phase. That means it introduces a positive phase component to the overall transfer function, means we will have a phase lead in the um, phase of the transfer function. So this is all about a quick recap of a lead compensator. So now based on that, can you identify which response is correct? So as far as amplification is concerned, which frequency do you think it will amplify? Low frequency component, low frequency signals or high frequency signals? If you observe the Bode plot, we have a high magnitude in the high frequency region and a low magnitude at a low frequency region. So it will attenuate the low frequency signals. Okay. So that means it amplifies the high frequency signals because we have a high magnitude in the uh, high frequency side. Now what about the transient response? Now from the pole zero location, what we can observe? We can observe that we have a pole in the left half plane, okay, and it is farther away from the zero. So if we have a pole in the left half plane and which is away from the imaginary axis, much away, then what can we say about the damping ratio? Will it increase or decrease? So if we have a pole which is away from the origin, that means our minus zeta omega and component will increase in magnitude if I talk about. Then what does it means? It means that zeta is going to increase, damping is going to increase. So that means we have increased damping, means there will be less oscillation in the response. Okay, and if we have less oscillation, that means we are going to have a quick response. A quick response means there will be uh, low rise time and also low settling time. So overall our transient response is going to get improved because we are having less oscillations and we are going to have a quick response. That means a low rise time. So that means the transient response is going to improve. That means which option we can confirm is correct? We will have an improved transient response and high frequency signals will be amplified. So option 2 will be correct. Okay. Now let's move to next question. So here we have a lead compensator which introduces an open loop 0 at -2 and an open loop pole at -5. Then the corner frequencies of the compensator will be at. It's a very simple question. We have just written the transfer function of a lead compensator, which was Kc into alpha. Now if we write in pole 0 form, it will be Kc s plus 1 by t divided by s plus 1 by alpha t. And what we are given? We are given that we have a 0 at -2. That means 1 by t is equal to 2. And we are given that we have a pole at -5. That means 1 by alpha t equals to 5. Okay. So where will be the corner frequencies? This can also be written as, okay, so this is in time constant form. So the corner frequencies will be 1 by t and 1 by alpha t. Okay. So now can you identify the corner frequencies? It will be 2 and 5 only. Any doubt? So for this problem, what will be the maximum phase lead? What will be the maximum phase lead of the lead compensator? We have the pole 0 location. From there, calculate the maximum phase lead. So if we draw the polar plot, we see that at omega equals to 0, we'll have magnitude Kc alpha of GC j omega we are talking, and at omega tends to infinity we will have again Kc. So these are the real and imaginary axis, and the polar plot or the Nyquist will look like this if omega varies from 0 to infinity. Okay, and here we have center at Kc by 2 1 plus alpha. Now what will be the maximum phase? Maximum phase will be the tangent to the locus from the origin. So this we have already done in the previous session also, how to calculate the maximum phase from the polar plot. So this will give you phi m. Now this will be 90 degrees, and this radius we know that it will have a radius of Kc by 2 1 minus alpha. Okay, now what will be sine phi m? It will be and Kc by 2 1 plus alpha, which will give you 1 minus alpha divided by 1 plus alpha. Okay, but we are not given the value of alpha in this question. How can we calculate the maximum phase? What we are given is the value of 1 by t and the value of 1 by alpha t. So if we divide 1 by t with 1 by alpha t, which will be equal to 2 by 5, so this t will cancel and alpha will be equal to only 2 by 5. Okay, so from here we can calculate alpha. Now we have alpha, calculate sine phi m, and from there calculate the angle phi m.
0.42.
0.42. Let me check. 0.42 is which value you are calculating? Sine phi m.
Yes.
Okay, so this will be 3 by 7. This will be almost 0.43. Now calculate phi m, which will be sine inverse of 3 by 7. How much you will get?
25.46.
Okay, so 25.46. Yes. Okay. So this will be the maximum phase which this lead compensator can provide. Okay. And calculate the frequency at which this maximum phase lead would be provided. What will be omega m? At which frequency this maximum phase will be given? So we have a formula for it, which is 1 by under root alpha t.
3.16.
3.16. Okay. So since we don't have values of alpha and t, but what we are given? We are given 1 by t equals to 2, and we are given 1 by alpha t equals to 5. Okay. So that means, sorry. Okay. So that means if you calculate 1 by square root t, it will be root 2, and square root alpha square root t, it will be root 5. And then if you multiply both, how much it will be? It will be 1 by under root t, which is under root 10. Okay, so this is what we have to calculate. This is nothing but equals to omega m, which will be 3.16 radian. Sorry, radian per second. Okay, any doubt? So from these
Clear.
relations we can calculate easily what will be omega by doing
Clear.
simple mathematics. Okay. Okay, now for problem 2, that is for this lead compensator, it is desired that the low frequency magnitude value in dB of the compensator's sinusoidal transfer function be 20 dB. Okay, we want that the low frequency magnitude should be 20 dB. What should be the value of Kc? Okay, so let's write the transfer function again so that we can calculate the low frequency magnitude. So Gc is nothing but Kc alpha 1 plus St and 1 plus St alpha. Okay, so what will be the low frequency magnitude? How can we calculate the low frequency magnitude? Do we have any pole or zero at the origin?
Yes.
We don't have any pole and zero at the origin. We have 0 at 1 by minus 1 by t and pole at minus 1 by alpha t. We don't have any pole and zero at origin.
Yes. Yes.
So our low frequency magnitude will just be 20 log Kc alpha. Okay, and this we are given that it should be 20. So log of Kc alpha should be equal to 1. That means Kc into alpha should be equal to 10. And how much is alpha? We have already calculated.
2/5.
So alpha was 2 by 5. That means Kc will be 50 by 2. That is 25. Okay. So answer is 25. If we had any pole or zero at the origin, so the initial magnitude, that is the low frequency magnitude, would be provided by that slope also. But since we don't have any pole or zero, because we have already seen the Bode plot of lead compensator, this is a straight line at low frequency region. So that means this magnitude is only provided by the gain of the Bode plot, that is the constant gain of the transfer function. So using that we have calculated the low frequency magnitude, and then we had the value of alpha, so Kc is easily calculated. Is this question visible or is it too small? Let me enlarge it. Okay. Okay. So in this question you are given a plant transfer function which is 1 divided by s into s plus 3, and it is desired that a lead compensator is used to design a unity negative feedback closed loop system. Okay, so using a lead compensator we have to design a unity feedback closed loop system, and it is given that the maximum phase provided by the lead compensator is 40 degrees. Identify the value of alpha. Very easy. We are given phi m, which is sine inverse of 1 minus alpha by 1 plus alpha, and this is given as 40 degrees. So using this calculate the value of alpha. So since this is calculated in radian, so first I think we need to convert 40 degrees to radian and then calculate alpha. Or we can use, just no need to do that, we can calculate sine 40 degree and calculate 1 minus alpha by 1 plus alpha. So how much is sine 40?
0.642.
0.642. So using simple mathematics you can calculate alpha by doing LHS and RHS thing. So alpha into 1 plus 0.642 will be equal to 1 minus 0.642. So alpha will be 1 minus 642 divided by 1 plus 0.642. How much is alpha coming?
0.218.
Okay. Okay, so this will be 0.218, which is almost equal to 0.22. Okay, so you are given the value of omega m, that is the frequency at which maximum phase lead is provided. Okay, for that omega m, calculate the value of t. So you are given omega m, which is equal to 10 radian per second, and you have alpha already calculated. So this is a very simple problem. Just use the formula for omega m, that is frequency at the maximum phase lead.
Zero point two one three.
0.213. Okay, so this will be equal to 1 by under root alpha t, and alpha we have already calculated. It was, so t will be 1 by 10 into under root alpha, that is 1 by 10.22, and if you calculate it you can get the value
0.213.
2143. Okay, so the nearest value is 0.215. Okay, what should be the value of Kc so that your static velocity error constant will be 10 per second? 10 per second. 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 10 So first tell me what is static velocity error constant.
Limit s tend to 0, s 0 of s, h of s.
Hmm. So it is Sg of s, h of s, and here your, so we have a compensator also. So this g of s is p of s into gc of s. Okay. So this kVe should be equal to 10 per second. Now we are given what values we are given? We are given the plant transfer function. Okay. So PS is 1 by s into s plus 3. And what is GCS? The lead compensator transfer function. It is Kc into s plus 1 by t and divided by s plus 1 by alpha t. Right? And Hs, we are given that we have a negative unity feedback, so Hs is equals to 1. So you have all the transfer function with you. Calculate the value of kVe as s tends to infinity, sorry, 0.
Alpha kc by 3.
It is alpha into Kc by 3. Okay. Okay. So if we multiply all these three transfer functions, what we will get? We'll have 1 by s into s plus 3 and s multiplied Kc s plus 1 by t s plus 1 by alpha t. Okay. And 1, there is no need to write, so these s will cancel out, and as s tends to 0, this will be equal to Kc, and so this 1 by t and 1 by alpha t will give you alpha and then by 3. Okay, so this will be the velocity error constant, and it is given that this should be equal to 10 per second. And alpha we have already calculated, which was 0.22. So Kc should be 30 divided by 0.22. How much it will come? You will get the value around 138. So this is how you can calculate all the parameters of the compensator using the design specification. So for that you need to remember how these design parameters are calculated and how these are related to the specifications of the Bode plot or Nyquist plot, etc. Okay, now since you have everything with you, alpha and t, calculate the open loop 0 of the lead compensator. So you don't have to calculate for the whole transfer function, you just have to calculate for lead compensator. So we know that for a lead compensator we have a 0 at minus 1 by t, and t we have already calculated, which was equal to 0.2143. So minus 1 by 0.2143. So this will give you value around, so just simple calculations. And similarly calculate the open loop pole. So this is located at minus 1 by alpha t, and minus 1 by t we have already calculated, it is 4.65, and alpha is I think 0.22. So you will get value around,
Ma'am, I didn't get the previous one, ninth one.
okay, this one.
Minus 1 by t is equal to 1 divided by 0.214.
So the value of t we have already calculated. So this was t for this question.
Now 1 by 2 itself is 1 by t itself is 2, no?
Sorry?
1 by 2 is 1 by t is 2 and 1 by alpha t is 5.
Oh, no, 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 no. This is different question. So that 2 and 5 was for the very first question. This one. It was for this one. Now we have a different set of question. So now we had this question where we were given the plant transfer function, and then we were given some design specifications. So we were given the maximum phase lead should be 40-degree, and we were given that the static velocity error should be 10 per second. So based on these two parameters we have calculated the value of alpha and t. So now we are solving for this alpha and t value. Okay, so the open loop pole will be minus 21.4 for this problem. Now since we have everything with us, again calculate the low frequency magnitude of this compensator. Okay, so for this compensator, calculate the low frequency magnitude. So we had alpha which was equal to 0.22, and Kc we had also calculated, that was equal to, I think, yes, it is 138. So your Kc alpha equals to 30. Okay. So what will be the low frequency magnitude? we have to calculate the magnitude of this low frequency region. Okay, again we have already calculated this type of question. So the low frequency,
31.62.
okay, 29. How much you are getting?
31.62.
31. Okay, let's
Yes,
see.
30%.
So in dB it will be 20 of log Kc alpha, and this is Kc alpha we have 30, so 20 log 30 we have to calculate. So whatever the value of 20 log 30 will be the answer. So it will be 20,
29.54.
yes, 29 point around 29.5 dB. Okay. Okay, so which is true about the lag compensator? So what is the purpose of using a lag compensator first?
Provide a phase lag.
Okay, and what else? So let's see how a lag compensator looks like and all its properties. So for a lag compensator, we have transfer function of a type Kc into beta 1 plus St divided by 1 plus St into beta, and here beta is greater than 1. Okay, so earlier we had the same transfer function in terms of alpha for lead compensator, and there your alpha was between 0 to 1, and the only difference is that alpha, which is here beta, is greater than 1. So what does it do? So here the pole and zero locations are exchanged. Okay, so now you have a 0 at minus, sorry, so this is pole at minus 1 by beta t and a 0 at minus 1 by t, because beta is greater than 1, so this will give you low magnitude pole location. Now since we have this type of pole 0, that means if we draw the total magnitude plot, so we will start with a 0 slope because we have no 0 or pole at the origin, so we will start with 0 slope, then we will get a pole first, so that will provide us a minus 20 dB per decade of slope, and then we will get a 0 which will contribute for plus 20 dB per decade of slope, so that means we will have a net effect of 0 dB per decade of slope. So this is how the Bode plot of lag compensator looks like. Okay, so here what can you comment about the low frequency and high frequency region? So for this is for lag compensator, and let's also draw for lead compensator, and it was like this. Okay, so this was about lead compensator. So in which frequency region we have a high magnitude in lead compensator? In high frequency region. Okay, in high frequency region we have a high magnitude, but here if you see in lag compensator we have a high magnitude region in the low frequency region. Okay, and similarly we have a low magnitude region in low frequency region for lead compensator and a low magnitude region for high frequency signal for lag compensator. So for lag compensator, which frequency component is it going to magnify? Because we have a high magnitude.
Low frequency.
Yes, so this magnitude is higher and this covers the region of low frequency. Okay, so statement 1 is not correct because it is saying that it magnifies high frequency component, but here we are seeing that it magnifies the low frequency component. And what about the second option? So second option is saying that it decreases the low frequency gain, but here what we are saying that it increases the low frequency gain, right? Because here we have a high gain, so it increases the low frequency gain. So second option is also not correct. What about the steady state error?
The pole is nearer to origin, therefore steady state error
Sorry.
computed. If the pole is nearer to the origin,
Yes, yes.
steady state error effect.
So for the steady state error thing, what we can observe that in the steady state the high frequency thing comes in the transient phase. So the steady state we only have low frequency component. So in the low frequency region what we can observe, we have a high magnitude, or what we can conclude that we have high gain. Now if we have a high gain, and if you remember the formulas for steady state error in terms of Kp, Kv and K alpha etc., all these terms are related to steady state error in a reciprocal manner. Okay, that is the steady state error is 1 divided by 1 plus Kp or 1 divided by Kv. So higher the gain, lower is the steady state error. So from here what we can conclude that since the gain is increasing, the steady state error will decrease, but here it is saying that it increases the steady state error. So this option is also not correct. Okay, and the last option is saying that it acts like a low pass filter. So low pass filter means it passes the low frequency component of the signal. From here we can also see that in the low frequency region it has a high gain, but for high frequency high frequency region it has very low magnitude. That means it attenuates the high frequency component, so that means it only allows for low frequency component. So the correct option is it acts like a low pass filter. Okay, so any doubt in this question? Okay, now let's move further. Okay, a lag compensator introduces an open loop 0 at minus 20 and an open loop pole at minus 2. Identify the corner frequencies. So we already know that corner frequency is nothing but the location of pole and 0. So what will be the answer? It is just 2 and 20. Okay, so uh, the corner frequencies are 1 by t and 1 by alpha t, and these are nothing but the location of pole and zeros. Okay, so it is 2 and 20. Okay. Okay, now we have a lag compensator where this T2 is greater than T1. Now what is T1 and T2 for a lag lead compensator? So if you recall the lecture, you will see that for a lag lead compensator, we write the transfer function as S plus 1 by T1 divided by S plus gamma by T1 into S plus 1 by T2 divided by S plus 1 by beta into T2. Okay, and here this gamma is greater than 1, beta is greater than 1, T1 and T2 are equal to or greater than 0. Okay, and gain obviously is greater than 0. So here that alpha which was here, we have shifted it to 1 by alpha is equals to gamma, so that's why this gamma is also greater than 1. So this part acts as a lead compensator and this part acts as a lag compensator. Now here you are given that the uh, 0 of a lag compensator, that is you are given, let me write, you are given T2 is greater than T1. So this is your T1 and this is your T2. Now what can we say about 1 by T2 and 1 by T1?
Sign changes.
So your 1 by T1 will be greater than 1 by T2. Okay. Now read the options and try to figure out the correct option. So both are the zeros of lead and lag compensator. Okay, so let's are you able to figure out? Okay, let's see. Now let's first consider the lead compensator. Okay, so let's consider the lead compensator first. So what are the corner frequencies of the lead compensator for this case? It will be 1 by T1 and gamma by T1. Okay, and now since uh, gamma is greater than 1, which value will be greater? Gamma by T1 should be greater than 1 by T1. Okay, now let's
Yes.
look at the lag compensator. So for a lag compensator, we have corner frequencies at 1 by T2 and 1 by beta into T2. Now for beta greater than 1, which will be higher? Your 1 by T2 will be greater than 1
But
by beta T2. Now let's see what options we are given. So first we have to figure out whether which one is the higher corner frequencies or lower corner frequency of the lag compensator. So if we see the lag compensator, which one is the higher corner frequency? 1 by T2. Okay, and so this will be your higher corner frequency. And for a lead compensator, which will be 1 by T1 will be your lower corner frequency, because 1 by T1 is less than gamma by T1. So among these two corner frequencies, your 1 by T1 will be the lower corner frequency for lead compensator, and for lag compensator 1 by T2 will be the higher corner frequency. Okay, and we know that it is given the question that 1 by T1 is greater than 1 by T2. So what does it mean? The lower corner frequency of lead compensator is greater than the higher corner frequency of lag compensator. Can we say that? Because we are given 1 by T1 is greater than 1 by T2, and 1 by T1 is the lower corner frequency of lead compensator, and 1 by T2 is higher corner frequency of lag compensator. Now let's read the options. So what we concluded lower corner frequency of lead compensator. So the lower corner frequency of lead compensator is here and here. Okay, and what else? We have a higher corner frequency of lag compensator. So the higher corner frequency of lag compensator are in these two options. So which is greater? The lower corner frequency of lead compensator. So the lower corner frequency of lead compensator is greater, so the last option will be correct. Read it and tell me if the last option or the second option will be correct.
Last option.
Correct? Any confusion?
No, ma'am.
Okay. Okay, now related to the Bode diagram of lag lead compensator, what can we conclude? It acts as a low pass filter or a high pass filter, or what type of frequency attenuation it does? So for that we need to
Option 3.
know the Bode diagram. So for a typical lead lag compensator, we have, sorry, so this will be the lag compensator part, and then we have a lead compensator part. Okay, so where we have high gain, so we have high gain in the low frequency as well as in the high frequency. So which part is attenuated? The intermediate part is attenuated, right? Because these frequencies and these frequencies will be passed, and what will be attenuated? The intermediate frequency, because we have low magnitude here. Okay, so which option will be correct? third option, that is the intermediate frequency band is attenuated. Okay, so now let's solve some more problems. So what was the last question we solved the previous lecture? Okay. Okay, consider the Bode plot, which is like this. Okay. And here is the phase. So this is 8 dB for a transfer function we are given, and this is the phase plot. Okay, so this is the origin 0, and at omega equals to 1 we have a phase of minus 60 degrees. Okay, so this is about a magnitude plot, G0 omega in dB, and this is your phase plot. So identify the transfer function. And the options are 2.51, 0.032s, e to the power minus 2.514s, 1.04, okay. Okay, so we are given the both a magnitude and phase plot. We have to identify the transfer function. Try it yourself first, then I will solve it.
I think option A, ma'am.
Option A. Okay.
2.51 is the magnitude and it's a negative slope decay.
Okay. Okay. Let's solve it. Okay. By looking at the Bode magnitude plot, what we can confirm is that we have gain type of transfer function. Only gain will be there, or whatever is it. We don't have any slope kind of thing. Okay. So that means the last option is ruled out, because here we, if this was the transfer function, then we will have a slope of minus 20 dB per decade because we have a pole here. So this option is not correct. Now all the options have a delay. Okay, so exponential with negative coefficient means that we have a delay in the system. So what is the magnitude contribution of exponential? So we know that any exponential, okay, because s we can write as j omega, can be written as cos omega minus j sin omega. Okay, and what is the magnitude of this? If you calculate the magnitude, it will be nothing but cos square plus sin square, that means equals to 1.
1.
So the magnitude contribution of exponential is 1. So the only magnitude contribution is coming from the gain of the system. So one thing is for sure, that the transfer function looks like something k into e to the power minus s into td. And in Bode magnitude plot, the so instead of transfer function, let's see, call it g of s. And what will be the magnitude of g of j omega in dB then? It will be 20 log k plus 20 log e to the power minus j omega td. And we have seen that this value equals to 1 and 20 log 1 is 0. So this term goes out. So we only have 20 log k, and this is given as 8. So how much is k then? So k will be 10 to the power 8 by 20. Okay, so if you calculate it, you will get 2.51. Okay, so the gain of the system is 2.51. Now another parameter that we need to calculate is this TD, and this TD you can easily calculate by looking at the phase plot. How can we calculate? What is the phase contribution, total phase of this transfer function? So we have g of s of the form k into minus std. G of j omega will be k into minus j omega td. Okay, so what is the phase of this system? So we have multiplication of two components, so the phases will be added. So what is the phase of a constant? It is 0. Okay, and what is the phase of exponential?
Omega TD.
Omega td, correct.
Minus omega
Minus
TD.
omega td, because this is nothing but theta. This is my
Yes,
e to the
minus
power
omega
minus
TD.
j theta. So the phase of this exponential is minus omega td. Okay, any confusion in this?
No, ma'am.
Okay. And this is given, so this is not given to us, but what we are given that omega equals to 1, the phase is minus 60 degree. Okay, okay, so this was g of j omega, and we are given that at omega equals to 1, we have angle of g of j1 equals to 60 degree. That means minus 60 degree, that means minus 1 into td is 60 degree. But remember that this is always given in radian. So what is 60 degree in radian? It is minus pi by 3. Okay, now can you calculate TD? It is just pi by 3. And how much is pi by 3?
One point zero four.
1.04. Okay. Okay, yes. So you can write it as 1.04. Okay. So what will be g of s? It will be 2.51 e to the power minus s into 1.04. Okay. So this is the transfer function for which the Bode plot is given to us. Okay. The correct option is D. Let's see some another problem. The question is the transfer function of a first order controller is GCS equals to K into S plus A, S plus B. The condition for this controller to act as a phase lead compensator is, the options are A less than B, A greater than B, K less than AB, and K greater than AB. This is simple problem. This you can easily solve. So how you should choose A and B such that this controller acts as a phase lead compensator. We know in a lead compensator we have 0 here and a pole here. So magnitude wise the pole is greater than the 0, and in this transfer function the pole is at B minus B. If we talk about magnitude, it is B, and the 0 is of the magnitude A. Which is correct?
A is less than B.
Yes, A is less than B is the correct option. Because to have a lead compensator, this should be minus A and this should be minus B. So B is greater than A. Okay. Now so this is the last question of today's session. The transfer function of a phase lead compensator is given by GC equals to 1 plus 3 TS divided by 1 plus TS, and T is greater than 0. The maximum phase shift provided by such a compensator is pi by 2, pi by 3, pi by 4 or pi by 6. So you have given the transfer function of a lead compensator. Calculate the maximum phase shift. So what is the maximum phase shift? Is equal to sine inverse 1 minus alpha by 1 plus alpha. Okay. Now how can we get the value of alpha? So by looking at the transfer function, what can you conclude about the value of alpha?
If alpha is equal to 1,
Alpha equals to 1. No. If alpha were equal to 1, then we will have a 0 at, let's see, GC is given as 1 plus 3TS and what is this? 1 plus TS. Okay, what is the standard form of phase lead compensator? Phase lead compensator. It is Kc into alpha 1 plus St divided by 1 plus St alpha. Okay. So in numerator we should have St.
Taking 3 common.
So if you take 3 common, then you will have, so let's see. If you take 3 common, you will have 3 1 by 3 plus St. So but this is not the standard form. Then what can we do? Okay, so let's see. So this t is given, but this t is just a parameter. Okay, so don't get confused with the t which is used here. Okay, so this is the general form that we write the lead compensator using parameters alpha and t, but that doesn't mean that this t always specify uh, the parameter that we use in lead compensator. What I am saying is, for the transfer function given to us, it is 1 plus 3ts divided by 1 plus ts, and we need to write it of the form 1 plus st dash divided by 1 plus st dash alpha. So if we are able to, any gain can also come here. So if we are able to write the left hand side uh, the one we have here on the right hand side, then we were able to figure out the alpha. Okay, so t is just a variable, so that doesn't mean that this is the variable which we have here. The standard form is this. So how can we get from here to here? We can say that this 3t is equal to some t dash, and this t is equal to alpha t dash. Can we do that? So this transfer function was given to us. I want to relate it with the standard form of the lead compensator, but the t given here, that doesn't mean that this represents the t of the lead compensator. Here this can be any variable. This is just a way of representation. We can choose any alphabet, alpha, beta, gamma, anything, a, b, c, d. So instead of t, because here this is not given us the actual form of lead compensator, we say that, let's say that we have this lead compensator. Okay, and to have this structure, this 3t should be equal to t dash, and this t in denominator should be equal to alpha t dash. Okay, from here can we calculate alpha? So we can divide 1 and 2, we can divide, so this will give us 3 equals to 1 by alpha, so that means alpha equals to 1 by 3. Okay, and t dash will be equal to 3t. So this is how the parameters of lead compensator looks like. Okay, so now if you write it in general form, so we have a pole at 1 by alpha t dash minus 1 by alpha t dash, which is minus 3 by 3t, that is minus 1 by t, and we have a 0 at minus 1 by t, which is equal to, and our t, sorry, at t dash, and t dash is minus 1 by 3t. Okay, so that means here is our 0, which is minus 1 by 3t, and here is our pole, which is minus 1 by t. And this confirms that we have correctly identified the poles and zeros, or the components, parameters of the lead compensator. Okay, so don't get confused with the variable given in the question. T here doesn't mean that this is the T of the lead compensator. Here they can use any variable. Okay, so instead of t, if it was something like 3ks or 3qs, so we just have to uh, relate it with the transfer function of the lead compensator, and variable we can choose anything. So if they have used t, we can use t dash or anything, and then we can equate. So by equating we get alpha equals to 1 by 3. Now can you calculate phi m? So it will be sine inverse 1 minus 1 by 3 divided by 1 plus 1 by 3. So this will give you how much? What will be phi m?
30.
So this will
30.
be 2 by 4. That means sine inverse of 1 by 2, that is 30 degrees, or pi by
30.
6. Okay. Any doubt in this question?
No, ma'am.
Okay. So that's all for today. There will be one more extra session that will be notified to you in this week. So, what you want to learn in the extra session? Should we solve more problems, or you want me to have some hands-on MATLAB? Whatever be the suggestion, I will take the class based on your suggestions.
MATLAB session.
So, a MATLAB session is fine to you also, sir?
Okay, ma'am.
Okay.
But,
Okay, so we will have a MATLAB session. So we will solve. Basically, that will be based on how to calculate the transfer function, or and Bode plot, root locus, everything. We will solve using MATLAB. Okay. Thank you.
is there any way, hello?
Yes, yes.
Is there any way that block diagram reduction is there, ma'am?
Block diagram reduction is not there in the course.
Oh,
So there will be one. There is one more course on control theory, I think. So that will run in this semester. In the next semester, I think there is block reduction.
that if can you, I mean, in MATLAB, is it possible that block diagram reduction techniques can be taught in this course?
Which topic?
Block diagram reduction.
Block diagram reduction. Okay, I will see how much I can cover. So I will try to cover as much as
Just one
possible.
program, just one reduction program using MATLAB.
Yes, yes. Okay. 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 Thank you.